Hey, Physics 112. All right, we're getting into what I consider just about the most complicated stuff that we do, and certainly the most non-obvious material. If we can get through chapters 30 through 32 and get through exam 2, I think we're really going to find the rest of the subjects in the rest of the semester to be a lot more accessible. But that said, we do have to get through these chapters. And these are incredibly important physical topics. Certainly for modern society, the stuff that we talk about in chapter 30 is essentially how almost all electrical power is produced in the world. The only situation where we don't use this type of system is solar power, which is a pretty small thing. But everything else, essentially, no matter what you do, nuclear, wind, anything, you use Faraday and Lenz's law to turn that into electrical power. So, chapter 30 is called Induction and Inductance. In chapter 29, we already did some sort of things where we were talking about induced, in this case, induced magnetic fields. So in chapter 29, we said that if you had a current, or currents are essentially just moving charges, right? Currents are just moving charges. If you have a current, this will create a magnetic field. And in fact, this is an induced magnetic field. Induction just means it's been produced because of something else you did. You forced it to exist. So we make the moving charges basically force a magnetic field to come into being. And so what we did this is still chapter 29, we said if we have a straight wire here, then we would get the direction of the magnetic field from right-hand rule 2, which is where we put our thumb in the current direction, and then we basically curl our fingers around for the magnetic field direction. So we'll call this the grab. You basically grab that wire with putting your thumb in the direction of the current. And so if I did that, if I had my thumb in the direction of current, my fingers would curl around, and this is a circular magnetic field. And so at the top, my magnetic field would be going in above here, and underneath the wire, my fingers would be curling back out, and so the magnetic field would be out below the wire. And so this is our induced magnetic field. If I have a circular wire, a circular current, or a curved current, then I could still use right-hand rule number 2, but there's also sort of right-hand rule number 3. Here you're going to, again, using your right hand, you're going to curl your fingers in the current direction, and then your thumb is the magnetic field direction. So here, my fingers are going to curl, this is my right hand, I'm going to curl them clockwise like this, and then my thumb is pointing in. So here, my thumb is pointing in. At the center of this coil. And again, this is an induced magnetic field, so I'll write it that way. All right, in chapter 30, what I'm basically going to tell you, and I admit you may not believe me, is that if you take just a coil of wire, so this is a coil of wire, so in other words, it's closed loop, so it actually, it's all connected, but there's no current in it, it's just a coil of wire. It's just you took a wire and you put it around a circle and connected it. And you bring a bar magnet towards it. This moving bar magnet is actually going to induce a current in my coil of wire. If I did exactly what I've got drawn here, where I have a north pole of a bar magnet coming towards my coil of wire like that, and say this is the front of my coil and this is the back of my coil. It's hard to really tell that, but so this is the front of my coil of wire, and this is the back of my coil of wire. And I basically bring this magnet towards it. What this is actually going to do is I'm going to get current that flows in that coil of wire where the current goes down here on the front, and it would move up there on the back, and it would be moving backwards here and forwards there on the top. I'm going to get coil current flowing in that direction because I brought the bar magnet towards it. I'm not going to touch the magnet with the wire. That's not what's making it do it. I'm actually inducing a current. So this moving magnetic field actually induces a current in the coil. This is called Faradays and Lenz's law. We can even sort of see that. I can move this magnet all on its own. It's not going to let me. Yes, it will. So as I move it towards it, I'm actually getting current to flow. As soon as I stop moving it, it stops. It's just when you move the magnet that you get it. But as soon as you stop moving it, the current stops flowing. So it has to be moving for current to flow. Yeah, so it has to be moving. So the actual equation, or one version of the equation that governs this or tells us this, is called Faraday's and Lenz's law. And it looks like this, where it says that there's an EMF, right? This is an EMF. We've talked about that before. It's an induced EMF, which is produced inside our loop of wire. Yep, loop of wire. And that EMF is what drives the current, right? So this is just saying, the EMF divided by the resistance in the loop that will produce the current that we actually see. If it's just a wire, there's not going to be very much resistance, so we'll get pretty big current. On the other side of the equation, there's a capital N over here, which just says that it's the number of times you loop the wire around. So if you just have one loop of wire here in this picture, and it's just equal to 1, in my simulation over here, I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Yeah, they have 6 loops of wire in this simulation. And obviously, if I increase the number of loops, I'm going to increase the EMF, right? This is like if this number gets bigger, that number should get bigger, magnitude-wise. And then there's this derivative of something with respect to time. There's this thing, and that's the real ugliness. And there's a negative out here, so let's not forget there's a negative. So officially, this quantity, this phi with a little subscript b, is the magnetic flux. It's the magnetic flux through the loop of our wire. And so let's look at this equation a little bit more. So from a qualitative sort of sense in terms of understanding what it's trying to tell us, because it isn't particularly obvious from that equation necessarily how we're getting this current to flow. First of all, the EMF if we make an EMF, we definitely are going to get current, right? An EMF is like a voltage source. And so if you have a voltage source, if you have an EMF, you're going to get current. And the larger your EMF, the larger the current's going to be. And this is just, again, the resistance in our loop. And this is Ohm's law. Just right here is Ohm's law. If N is larger, right? If N is larger, then we have a larger EMF. And so again, we can increase if we increase the EMF, we increase the current. And we can get more if we loop the wire around multiple times. Now the time derivative of the magnetic flux through the loop. So first, the magnetic flux is analogous to the electric flux, which I know you guys didn't enjoy from back in Gauss's law. But as we remember back when we did Gauss's law, most of the time that equation turned into a much simpler looking thing. Instead of having that integral, we really just had a much simpler integral where basically we said it was just the electric flux, the electric field times the cosine of an angle in an area. And that's what we're going to have here again. So our magnetic flux is going to be the magnetic field times the cosine of an angle times an area, where that angle is once again going to be the angle between this area vector to our loop and the magnetic field. So for my loop here in my drawing, the area vector essentially points perpendicularly like this. It points perpendicular to the plane of the loop. So we can imagine this loop has got some plane like this. This area vector has an angle which is perpendicular to that plane. And so there's an angle between that area vector and the magnetic field. That's our cosine. That's the cosine. That's our theta that goes into that cosine. And we'll see that what that angle is a little bit better when we're doing actual problems. But as long as our as we can bring things out of that integral, as long as that magnitude stays constant when it gets dotted into the area factor. So most of the time, this is what we have for our magnetic field, magnetic flux. And so it's just whether or not there's a variation with time of the magnetic field, the cosine of the angle or the theta between the magnetic field and the area vector and the area vector itself, the amount of the area. If they don't vary with time, if the derivative of this is equal to 0, then EMF is equal to 0. So if the magnetic field is constant the whole time and theta is constant the whole time and the area is constant the whole time with time, then basically you have a 0 EMF because there's no derivative of the flux with time. But if any of them are changing, if the magnetic field is getting stronger, if the theta is changing, or if the area is changing, then we're going to get an EMF, and that means we'll get a current. So again, here's our equation. If we want to talk about it in terms of current, since current is just the EMF divided by the resistance, we just take the EMF equation and we divide it by resistance. So let's look at number 7 really quickly, and then we'll take a break for the next video. So here I have a loop. I have this circular loop, mostly, and it's connected down here with the resistor, and it's in a region where the magnetic field is coming out, right? There's a magnetic field out in this region. That's what the little dots are telling me. And it tells me that the magnetic flux, there's an equation for the magnetic flux, which is 6t squared plus 7t. By the way, I should have said this back here. Unit-wise, a magnetic flux is it's a Tesla for the magnetic field, and then a meter squared for the area, and that's officially a Weber, which is a W little b. Like the grill. So here's my equation for the magnetic flux as a function of time, and that's where this is actually written in, this comes out in milliwebers. So it's not, in other words, this is a 10 to the negative 3 Webers. We should keep that in mind. And it says, what's the magnitude of the EMF in the loop when t is equal to 2 seconds? So let's worry about that before we worry about part B. So A, we want to say the EMF is negative we just want the magnitude of the EMF right now. So we're going to say, we're not going to worry about, let me erase this all. If I just want the magnitude of the EMF, then all I need is N dB dt. Well, N is equal to 1. This only loops around one time. So it's 1, and then I'm going to take the derivative of this with respect to time. So I'll actually write that out. So I end up with 12 times t plus 7. And then at time equals 2 seconds, that EMF magnitude is 24 plus 7, which is 31. And that's milliwebers. So 3.1 times 10 to the negative 2. Sorry, that's milliwebers. It comes out. Oh, goodness. Just a second. Well, let me erase all this. So if that was milliwebers times. Just a minute. Okay, so it does come out. This is actually a millivolt. Let me go ahead and prove that to you. So basically, we'll just do, so a Weber is a Tesla meter squared. A Tesla was a Newton second meter per coulomb. And so if we plug that in for Teslas here, we have a Newton second meter coulomb times a meter squared. So we can get rid of one of these meters. Oh, and I'm missing a second somewhere. Oh, good Lord. My seconds went away somewhere. Right. So then here I have a Newton meter per coulomb times a second. But when I take this derivative, when I take the derivative of our flux with respect to time, this actually becomes, oh goodness, this over here would have come out, would have been a Tesla meter squared per second. And so, and a Newton meter per second, this is a volt. This is a joules per coulomb. In any case, you probably don't care, but it is, our units do come out to be a millivolt in that derivative, which is good because this is an electric potential or an EMF, and it should have units of volts. So that's our part A. The EMF is that the current, and it isn't asking us for the current, but we could figure out the current. No, we can't because we don't know the resistance. But if we did know what the value of this resistance was right here, we could get that the current was our EMF over that resistance. Now, part B asks what's the direction of the current to the right or to the left. So it's asking us, in this resistor, does the current go this way or does the current go that way? And that is actually what the negative is for in Lenz's law, or in Faradays and Lenz's law. The negative in the equation is actually the Lenz's law part of it. And I'm going to cover that in the next video.